Hello. Now we are going to look at doing some problem solving with right angle triangles. So there'll be some language, there'll be some English involved in this style of question, and we also have to be able to take all of the tools that we know about and see if we can apply them in a more complicated situation. So we'll start off with the language that may come with these questions. So if we have a horizontal line, so a line going along the ground, and we rise up from that, so say we're looking up at the top of a building or the top of a hill, we're rising up from the horizontal, we call that the angle of elevation. To elevate something is to bring it up. The opposite to that would be an angle of depression. So a depression is like a hole in the ground. So if we are dropping down from the horizontal, we have an angle of depression. And they can use this language in questions to tell us whether we're rising or falling. So we have angle of elevation going upward from the horizontal and angle of depression going downward from the horizontal. Connected with that is to look at what the tan of an angle to the horizontal would be. So if we have a horizontal line and then we're rising by a particular amount, which I've labeled y, like x and y in our coordinate system, the tan of this triangle would be y all over x, the distance across divided into the distance going up. Well, if we have the distance going up divided by the distance across, that's the same as rise over run. That's the same as the slope of our hypotenuse line. The slope of our slanted line here would be given by the tan of our angle, rise over run. And this connection between the tan of the angle to the horizontal being the same as the slope of this line will be an important idea in the long run. So we need to know if we have a horizontal and vertical sides of our triangle, the slope of this hypotenuse line comes from getting the tan of the angle, because we can see that they're mathematically the same when we draw it out. Now let's have a look at some questions where we're given a big English story, and then what we're going to do is draw some diagrams, write down the tools we have in terms of our formulae, and then we'll be able to solve the problem. But we have to take the story that we're given in English, and we have to use diagrams and our equations, the tools that we've got, to figure out what we need to do in order to get the answer. So from 10 meters away, say we're across the street from a building, a second story window has an angle of elevation of 20 degrees. The third story window is a further 9 degrees up. How tall is a story of this building? Well, there's a lot going on here. So we know we're 10 meters back from the building. And then we know, initially anyway, we're going to have an angle of elevation of 20 degrees up to this second story window. And then we go up another 9 degrees to get to the next story's window. So can we draw that out? So we know that we are 10 meters back, so 10 meters along the ground. So we're standing over here and we're measuring our angle, we'll say, from the ground. The question may tell us that we're standing up at a particular height and we'd have to take that into account. But for right now, we don't mind. We're just measuring along the ground 10 meters to the foot of the building. And then we rise vertically upward. And to get to our second story, so our second story, well, if it's the second story, we might call it H2, so the height up to the second story. And our angle going on up to here is 20 degrees. And then we go 9 degrees further. So it's not that we're 9 degrees up from the ground, we go 9 degrees further. So if we go up 9 degrees further to the next height, then we'd be going 9 degrees up from this line here, from where we were. We go 9 degrees further. And we're still on the same vertical building. So we've gone 9 degrees up here. So it's an angle of 9 degrees there. And that's going to bring us up to the window of the third story. So that total height there is up to the height of the window in the third story. So now we've taken our story that we were given here and we have drawn out that information in a diagram. And I can see that I have effectively got two right angle triangles here. I have the one drawn in orange and I have one that's partly drawn in blue. But it's better to break up these situations so we can see each individual diagram that we've got, because we've got two right angle triangles and it would be better if we drew them out. So we have a right angle triangle, the lower one, that goes up by 20 degrees. And it's 10 meters back. It's got a height up to the second story. And then we have our bigger triangle. I drew that one in blue. Sorry. Now I've drawn out both of these situations. I say, well, how can I find how tall a story of this building is? Well, if I can find the height to a given point on one story and the height to the same point on the third story, the difference between those would have to be the height of a story. The height I am looking for would have to be the height of the third story minus the height of the second story. So I need to find H3 and H2. I need to find the height of the second story, height of the third story, subtract them, and that gets me the height of a story of the building. Now that's very difficult to figure out from the English, but once we draw the diagram and we say, well, I'm looking for this distance here, I can see that subtracting these two things must give me that distance that I am looking for. So drawing the diagram is absolutely critical to being able to answer these questions. Now, how do we find H2 and H3? Well, I have right angle triangles, so I immediately say, well, I know the tools that I need for right angle triangles, or that I have for right angle triangles, so I'm going to write them down so I can see all the tools available to me. And my main tools for right angle triangles are sine, cos, and tan, and Pythagoras. And every time I'm trying to deal with these questions, I physically write those tools down so that they get embedded in my memory, so that when I need to use them creatively like this, they are available to me without me having to think about them too much. So now we have this, we say, well, I have an angle and I have the adjacent side. So I have the side that's next to my angle that I know about is my adjacent side. The side across from me, across from my angle, is the opposite side. And then the side across from the right angle would be the hypotenuse. And likewise here, this would be our adjacent to the 29 degrees, opposite the 29 degrees, and the hypotenuse of our second triangle. So now what we can do is say what one of our tools connects the angle, the adjacent, and the opposite together. Well, I can see that that would be the tan function. So tan is what I need. So tan of my angle is going to be opposite over adjacent. So I can do that for both of my triangles. So I have tan of my angle 20 is equal to H2, height to the second floor, divided by 10, which is my adjacent. I need to get rid of this fraction, so I need to multiply both sides by the lowest common denominator, which in this case is 10, because the denominator here is just 1. And then when I've done that, I have 10 times tan 20. Remember, writing 10 next to tan would mean that it's 10 multiplied by, just like 10x would mean 10 multiplied by x. I have 10 divided by 10 is 1, so I'm just left with H2 here. Then I go to my calculator and I find out what tan of 20 degrees is, and I go to 4 decimal places, so 0.36397. I've actually gone to an extra decimal place there, but go to at least 4 decimal places. And that's H2. And I multiply that up and I get 3.6397 for the height of the second story. And I do the same thing for H3. Now I have both H2 and H3. I just need to subtract them in order to find the height of a single story. So I have 5.5431 minus 3.6397. In this case, it works out to about 1.9, and the units I am dealing with in this question are meters. So for my final answer, I'm definitely writing down meters. Next, find the slope of the ramp. So here we would be assuming this is a horizontal line and this is a vertical line, and then we have the slope that we might drive up onto. So the slope we know would be the angle to the tan of the angle to the horizontal. So if I called that theta there, and this is my vertical height, so I might call that y, just like this would be my distance across x. So my slope would be y over x, or tan of theta. I could do it either way, and we're going to do it both ways. So if we did this via just finding the slope directly, we know that the slope would be the rise over the run. Run would be y all over x. We'd need to use Pythagoras in order to find our missing side. So let's do it that way first. So we know the side across from the right angle is the hypotenuse. So we write down our formula, sub everything in brackets, and carefully work on down until we get y is 2 root 11. That means that our slope would be y all over x, would be 2 root 11 all over x. Our difference in x is 10, and that simplifies to root 11 all over 5. Now that's a very exact answer. It tells us with as much accuracy as we would like exactly what the slope is. The other method we could go for is to find the angle using the information that we're given. We have the adjacent and the hypotenuse, so we'd be able to use cosine to find the angle, and then getting tan of that angle will also give us the slope. So we'd have cos of theta is 10 all over 12, adjacent over hypotenuse, and then we'd need to take inverse cosine of both sides to undo, to get rid of the cosine function. So we would be left with just theta. Now that we know the angle theta in here, we are able to just say, well, the slope is going to be equal to tan of that angle, the angle to the horizontal. And we get that tan of the angle is 0.6633, and it keeps on going. And you know that we have rise over run, so we could write that in as being over 1. Now this method is perfectly mathematically correct. However, the method using Pythagoras gives you a more exact answer that is easier to use in later parts of a problem. So it is essential that we know we can do this, that we can find the angle and then get it, tan of it in order to get the slope. That is critical. We do need that tool available to us as a fact that we know, because it's necessary for certain types of questions. However, if we can, it is often better to use Pythagoras because it gives us an exact answer. If you put this into your calculator, you will get an almost identical decimal, but you can work with this much more effectively. So in general, Pythagoras is the better tool for getting the answers that we need. However, knowing that tan of the angle to the horizontal is the same as the slope is very important in the long run. So we can see in this, what we always have to do is take our diagrams, fill in any information that we can, draw any extra diagrams as clearly as we can, labeling in our right angles and so on, write down all of the tools available to us, and then once we've done that, we'll be able to see how to make a next step. Even if we can't see how to finish the question, by drawing out the diagrams, by labeling everything that we know, and by writing down all the formula that we know for these shapes, you will always be able to see a next step that we can make. And once you can make a next step, then you're likely to be able to make another step. But this structure of read the question, carefully draw the diagrams, write out the formulae, and then see what formula you have that connects the information you've got in your diagrams is how we get unstuck with these questions. And that's what we need for now.